Now, welcome back again, dear students. Electromagnetic induction, lesson 9. This is a small theory. In lesson 8, we learned about the self-induction of a coil, how it was when you were trying to increase the current in a circuit and there was an inductor, it was trying to oppose it. And when you were trying to decrease the current in a circuit and there was an inductor, it was also trying to oppose it. Means it was acting as an electrical inertia, and the EMF was equal to minus L dEI by dt. That is what we learned in the previous lesson, EMI 8. Now, where L was called the coefficient of self-inductance, right, or the electrical inertia. Now let us find out the L, coefficient of self-inductance of a long self-inductance L of a long solenoid. Now look at the first diagram. This is a coil. This is a coil. Current entering from this side, leaving from this side. It can enter from this side, can leave this side. And this is a solenoid with air core. Means inside the coil, there is no material medium, it is filled with air, right? Now look at the second diagram, second figure. Look at the second figure. This yellow part you see is a magnetic material, like you can say iron or stainless steel or soft iron. And around that, this coil is going around like this. Okay? Going around like this. And each turn is not a circle. In fact, it is an ellipse. It is not like this. It is like this. It is like this, an ellipse, right? So, the second one is a solenoid with some magnetic material. This yellow figure indicates this is some magnetic material, either iron or a soft iron or stainless steel or steel. Now, this will be called a long solenoid if its length as compared to its radius. Length is very, very greater than r, its radius. Then it will be called a long solenoid. And in previous lessons, in magnetic effect of current, we derived due to a solenoid carrying current. This will be called a solenoid if it is carrying current. Otherwise, if it is not carrying current, then it is just a spring, you know. So, in the magnetic effects of current, we derived for a coil like this called a solenoid carrying current at the center, the magnetic field B was equal to mu naught n I over L, where L was the length of the solenoid from here to here. N was the total number of turns, not the number of turns per unit length, the total number of turns. I was the current, and mu naught the absolute permeability of vacuum. Because the inside is air, it was used mu naught. And we also know from electromagnetic induction flux, symbol phi, magnetic flux. That is number of lines of force passing through an area normally. If it is not passing normally, then you take the dot product, that is B dot A, that becomes BA cos theta, then the lines of force becomes normal to the surface. This was the flux passing through in one turn. So if the coil, if the solenoid has n number of turns, then the total flux phi will be n times this. This is the flux through one turn. If it has n number of turns, then the total flux will be this in n number of turns. Now let us then come back to the next phase. So now by putting the value of B, so the flux becomes n times, this was your B, which you derived in magnetic effects of current, mu naught n I over L, A cos 0. Then how do I write cos 0? How the angle is 0? So let me explain that. First, then we'll come back to this line. Okay. So let me go back. In magnetic effects of current, a wire carrying current I from here at a distance r, the magnetic field induction, small magnetic field due to this small element called IDL was mu naught over 4 pi IDL sin theta over r square. For a straight conductor carrying current I at a perpendicular distance r, here the magnetic field induction B was derived like this. If you look at my previous lessons, and if this angle is alpha, this angle as beta, then this expression was converted to cos alpha plus cos beta. And for a circular wire carrying current at the center, this was the magnetic field we had derived. B was equal to mu naught over 4 pi I over r times 2 pi, this total angle. Now, and I have also explained you time and again, I am explaining how theta is 0. Suppose this is the coil. This is the coil through which current I is passing through. Now, if you look from this side, suppose the direction of current from this side is clockwise. So, this side of the coil behaves as the south pole of a magnet. So, automatically from this side, the direction of current in the coil will be anti-clockwise. So, it will behave as a north pole. Means the whole coil carrying current, because a single coil carrying current was having a magnetic field. There are many such coils, many such turns. So each turn is producing a magnetic field like this. And this side is north, this side is south. So the magnetic field lines are this. These are the magnetic field lines starting from north, going like this, and arriving at the south and passing through the magnet from south to north. Similarly, these lines. So a coil carrying current behaves as a magnet. One side behaves as south, or other side behaves as north. So these lines, if you look from this side, these lines are passing through this area. I take a single turn, passing through this area normally. So theta is 0. If this area is pointing to this side and magnetic induction B is to this side, so both are in the same direction, therefore theta is 0. So through all the turns, angle between B and the area of each turn, theta is 0. Right? Theta is, sorry, the figure was not visible. Let me explain once more. This is a coil carrying current. If from this side the direction of current is clockwise, this side of the coil behaves as a south pole. From this side it is anti-clockwise, this behaves as north poles. Therefore this coil behaves as a magnet. Therefore these are the magnetic lines of force originating from north and going like this, passing through the magnet from south to north. So, and if you take one such area like this area is pointing this way, and these field lines are entering this way. B is this way, area is this way. Therefore, theta is equal to 0 degree. So, that is how I explained here. Theta is 0 degree. So, your flux is equal to cos 0 is equal to 1. So, it becomes n into n square mu naught I A over L. This is the flux due to the long solenoid, right, which is carrying current I, where A is the area of each turn, capital N is equal to total number of turns, N is equal to length of the solenoid. Since it is air cored, so it is mu naught. That is permeability of a vacuum that we will study in magnetism. Like in electrostatics, you did force in vacuum was equal to 1 by 4 pi epsilon naught Q1 Q2 over R square. In magnetism, we will study, this was the force between two charges. In magnetism, we will study force between two magnetic poles will be mu naught by 4 pi M1 M2 by R square, where M1 M2 are the pole strength of two poles. Very similar. This is the permittivity of vacuum. In magnetism, we will call this permeability of a vacuum or empty space. And from previous lesson, that was electromagnetic induction 9, we also learned the self-inductance of a coil. The flux associated phi was equal to I explained phi was proportional to I, so phi was equal to some constant into I. That L was called the self-inductance. And how the self-inductance was acting in a coil, if the current was increasing, if you are trying to increase the current, it will oppose by creating an EMF. If you are decreasing the current, it will oppose the decrease by creating an EMF which opposes it. So this is the flux. In this way, this is the flux from the previous lesson. Therefore, these two are equal. Therefore, Li is equal to mu naught n square Ia by L. Li is equal to mu naught n square Ia by L. So I cancels. So I am left with L is equal to mu naught n square A over L. Is the self-inductance of a long solenoid whose length is more as compared to its radius, and the core is vacuum or air. If the core is vacuum or air. If the core is not air but some other magnetic material, like in this case, here the core is vacuum or air. Here this yellow part is a magnetic material, either iron or stainless steel or some other magnetic material. The coil is wound around it. Then in this case, what will be the self-induction? So, so this mu naught has to be replaced by the permeability of the material of that medium. Means to what extent mu naught, this yellow one, which is a magnetic material, to what extent it allows the magnetic lines of force to pass through it. That is called permeability. We'll discuss much about that in magnetism while studying magnetism. So if the core is not vacuum, this has to be replaced. So if the core is not air but some other magnetic material, then mu naught is replaced by mu, permeability of the material. So the self-inductance, let it be L dash, it becomes mu naught mu r n square A over L. Now what is the conclusion from this or this? What is the conclusion? Now what is the conclusion? L is in the denominator. So if length of the solenoid increases, this decreases. A is in the numerator. If A increases, this increases. If N increases, this increases much faster because there is a square term. So the conclusion is self-inductance of a long solenoid L is proportional to 1 by L. Means if L is more, L is less. Because it is in the denominator, this is a fraction. A is in the numerator. So if A is more, L is more. Means means if this and this both have the same length, the number of turns here and the number of turns here are same. Here the area is more, here the area is less. So the self-inductance of this, let it be L1, let it be L2. So L1 will be greater than L2. Because N and L remaining same, more the area, more is the self-inductance. That is from here because A is in the numerator, right? Now then L is proportional to N square. So because N square is in the numerator, means if N becomes 2N, your L becomes, when N is N, L is proportional to N square. Of course, L and A are remaining same. When number of turns becomes 2 times, then L will be proportional to square of 2N. That is equal to 4N square. So this is equal to 4 times the previous L. Let it be L1, let it be L2. So L2 will be equal to 4 times L1. So because there is a square term, right? So I hope it is clear. We have 2 more lectures to finish electromagnetic induction. Then we will move on to current electricity, alternating current. That will require only 5-6 lectures to finish because all derivations are just mathematical. No such explanation is required, but still I will explain you. Okay.